Hello everyone, thank you for coming to this talk. So yeah, we are going to talk about the meeting of algorithm design and big data. So what we are going to learn in this talk is some fundamental trade-offs about that govern MapReduce algorithms or big data algorithms. We'll focus on map, but it's not necessary. And also some techniques to design efficient algorithms for big data applications. So let's see how we do it. So here's the outline. We will first look at some fundamental trade-offs with an example that clarifies it. Then we'll look at 3 techniques, and we'll illustrate each technique using an example. And then we'll conclude. So let's then just jump right in. So the first example that we'll look at is the drug interaction problem. So here's the setting. The setting is that we have 3,000 drugs, and we have 1 million patients. These are the data has been collected over 20 years. And for each drug, we have a record which is around a megabyte of data, which shows over these 20 years which patients took this drug, what were the diagnoses for those patients, what was their case before they took the drug, what happened to them after they took the drug, all of that. And what we want to find, what we want to figure out is if any pair of drugs have negative interactions. So let's see. So here's a simple MapReduce algorithm for it. So I'm assuming that everyone in this room is familiar with MapReduce. So the input to the map is a drug I as a key, and its record Ri as the value. And then what the map outputs is that for any other drug J, it outputs Ij as a key and Ri as the value. So if I is 1, J can be like anything from 2 to 3,000. So it outputs all of these. And then what the reducer receives after the shuffle happens is that for each pair of drugs I and J, it receives the value which includes the record for drug I and the drug J, and it just computes the interaction between them and outputs it. So let's see it in action. So let's say here in this example we have 3 drugs. The mapper for drug 1 outputs the key 1, 2, and the value drug 1 data. So you don't hear it? Like if I walk over here, do you guys still hear? You don't? Oh, okay. All right, so we'll just stand here. So yeah, and then it also outputs the key 1, 3, and the drug 1 data. And similarly for the other mappers. And then the shuffle happens. And then the reducer receives these key value pairs, and then they just do their job, okay? So it's a pretty simple algorithm. Let's see the total amount of work. So we have 3,000 drugs, so that means 4.5 million pairs of drugs. Let's say each pair takes 100 milliseconds of computation to compute the interaction between the pair. So that's a total of 120 hours of work. And if we distribute over like 10, 16 core machines, it's going to take less than an hour. So it's pretty good, right? I mean, it's a very simple problem, very simple solution, pretty efficient computationally. So everything is good, right? Well, not so much. Let's look at the network communication. So we have 3,000 drugs. Each drug causes 2,999 key value pairs to be emitted by the map. And each drug is contributing a megabyte of data to each such key value pair. So that's a total of 9 terabytes of data. And to get a sense, it takes over 20 hours worth of network traffic over a standard 1 gigabit per second Ethernet, which may not be too bad for some applications, but for this applications, like the data fits on the memory of this laptop, so it's pretty small. So this is not really acceptable because we have like 3,000 drugs, 1 megabyte of data per each drug, so it's like a total of 3 gigs of data. So let's see if we can do better. So here's an idea. The idea is that we group the drugs together. So let's say in this case, like as an example, we group the drugs into 30 groups of size 100. And let's say that GI is a group for drug I. Then the algorithm works as follows. The map again receives the drug and the record. What it outputs now is the group for drug I and any other group G prime, which as the key. And then as the value, it outputs the drug and its record. Notice that the information about which drug this record belongs to has been lost in the key, so we are just putting it in the value. So if like GI over there is like 1, this G prime is going to be like anything from 2 to 30. And then what the reduce receives is that for any pair of groups, it's going to receive the 200 drugs in these 2 groups. And it's going to compute all the pairwise interactions between any drug in group G and any drug in group G prime. So very simple. So the total amount of work in this algorithm is exactly the same as before, because each pair of drugs is getting compared only once. So it's the same as before. It's pretty good. And now we are actually good, because we have 3,000 drugs, and each one is causing 29 key value pairs to be emitted. And each drug is contributing a megabyte of data to each such pair. So that's a total of less than 90 gigabytes of data. And it's less than 15 minutes on a standard Ethernet. So let's look at this algorithm a little bit more closely. So there's a trade-off in this algorithm. Let's say instead of 30 groups, we do this algorithm with n groups. Okay? So then what is the number of key value pairs emitted by the algorithm? Well, each drug needs to get paired with any other group. So that's n minus 1 groups. So that's the number of key value pairs emitted. And what is the number of input records to each reducer? Well, each group is of size 3,000 over n. And each reducer is receiving 2 groups. So that's 2 times 3,000 over n. So if we increase n, 2 things happen at the same time. The number of key value pairs emitted by the map, and as a result, the amount of communication used by the algorithm goes up. On the other side, the reducers that we use, the size of the reducers that we use are going down. And we are getting more parallelism. So what this means is that the more parallelism that we want out of this algorithm, the more communication we'll have to pay. The more communication costs we'll have to pay. So let's see if this trade-off is only specific to this algorithm, or is it like a little bit more fundamental. So to see that, let's define a notion of reducer size, which is the maximum number of inputs a reducer can receive, and we denote it as lambda. Okay? So now let's analyze a drug interaction problem. So in this slide, we are not analyzing any specific algorithm about this problem. We are analyzing the problem itself, like what is the requirement of the problem. So let's assume that we have D drugs. Previously it was like 3,000. Let's just generalize it. So each drug needs to meet D minus 1 other drugs, because we need to compute the pairwise interactions for each drug with any other drug. And at each reducer that this drug gets sent to, it meets at most lambda minus 1 other drugs by the definition of lambda. So each drug needs to get sent to at least D minus 1 over lambda minus 1 reducers. Okay? So what does that mean? That means that the minimum amount of communication that any algorithm that solves this problem would need is D times D minus 1 over lambda minus 1, which is almost equal to D squared over lambda. And this exactly shows a trade-off inherent in this problem. Because lambda is, so the further you increase lambda, the more work you are doing per reducer, and the less parallelism you are going to get. And here it shows that the more you increase lambda, the less communication you also have to pay. So this trade-off between parallelism and communication is inherent in the problem. It doesn't have anything to do with the algorithm. And how well does our algorithm trade off against this lower bound that we have, D squared over lambda? Well, with n groups, the reducer size is going to be 2D over n, because the size of each group is going to be D over n, and each reducer is receiving 2 of those. And the communication is D times n minus 1. Each drug gets paired with any other group. Okay? So that's almost equal to 2D squared over lambda. If you solve for it, if you solve for n, from here, let's see, from here, then you get this amount of communication. So it's like within a factor 2 of the lower bound that we obtained here. So this means that this algorithm that we have, the trade-off it's getting is within a factor 2 as good as any other algorithm. And if you think a little bit more carefully, you can actually remove this factor 2 as well, but I'm not going to go into that. So this example shows us teaches us 2 lessons. The first one is a fundamental trade-off that exists in MapReduce. And it is a trade-off between communication and parallelism. So it is in general true, like it is not only even specific to this problem, that the more parallelism that you want, the more communication costs you have to pay. So, and you can actually formulate it based on the parameter reducer size that we introduced. Like in the case of the drug interaction, if you have the reducer size to be lambda, the time complexity of each reducer is lambda squared, because it's computing the interactions between any pair of those lambda drugs. The space is proportional to lambda. The communication, we showed that is proportional to 1 over lambda. And such a formulation can actually help to optimize several things. Like you can use it to optimize the wall clock time of the algorithm based on the characteristics of your cluster, of your computing cluster. Or you can use it like to optimize the cost of running the algorithm on EC2. So this was the first lesson out of this example. The second lesson is this technique that we just saw, the grouping. And what it does is that it decreases the key the resolution of the key. It sends more data to each reducer. And as a result, it trades off communication with computation. So it lowers the amount of communication at the cost of parallelism. But the thing is, like in this first example that we saw, the grouping was pretty simple. Like we just like grouped the stuff together. But it may not always be as trivial. So let's look at an example which is somewhat more interesting. So it's a problem of similarity search. And it comes up in a lot of applications, like in near duplicate detection. Let's say you have like web pages. You want to figure out which web pages are nearly duplicates of each other so that you don't show them, you don't show the duplicates in search results. Or in document topic classification, you want to figure out which news items belong to the same news story. So it comes up everywhere. And we'll particularly focus on the problem of many-to-many similarity search, in which we have n data objects. So these can be, for instance, these can be the images posted on Facebook in the last week. And m query objects, so these can be the images posted on Facebook during the last day. And our goal is that for each query object, we want to find the most similar data object. So for each image that was posted since yesterday, we want to find the most similar image that was posted since last week. So the main problem here is that of candidate generation. So let's say we have 10 million data points and 1 million query points. So if you want to just do brute force candidate generation, we'll have like 10 to the 13 pairs of data and query objects to look at. And even if we take 1 microsecond per pair to see if they're actually similar, it is going to take 116 days of computation. So even if we distribute like over a cluster of 50 nodes, it's going to take more than 2 days. So there is a big idea. It is a big idea in like computer science in general. I mean, it's that of locality-sensitive hashing, which allows us to do a lot better than what we just saw. So the idea is the following. The idea is let's build and use hash functions which are likely to map similar objects to same buckets and dissimilar objects to different buckets. So they are hash functions, but they're kind of different from typical hash functions because what's an ideal hash function? An ideal hash function is just like uniformly random. But this is a little bit different, so it sends similar things to same buckets and dissimilar objects to different buckets. So how do we do this? Actually, let's see, like, if you have such a hash function, how do we use it? So if you have such a hash function, the way we generate the candidate pairs is that we just look at the objects that have gone to the same buckets. Okay? So if 2 objects have gone to the same buckets, that's a candidate. If not, they are not. So that's how we can use these hash functions. And it breaks down, it reduces the search space significantly. So let's see how we can do it. Let's say these are some data points that we have in some d-dimensional Euclidean space. So they can be like d features of the data objects that we have. Then to build such a hash function, here's one way to do it. So we pick a random line in this space. Then we partition this space into stripes in perpendicular to this line, and we assign each of those stripes a number, like 0, 1, 2, 3. On the other side, this can be like -1, -2, -3, and so on. And each of these objects get mapped to the idea of the stripe. Like these objects get mapped to 0. These objects get mapped to 1, and so on. But we don't do this just once. We do it multiple times. Like here is a second time. So we pick another second line. We do these partitions. And now each of these cells is a bucket. Okay? And each of these cells has an ID, which is the IDs of those 2 stripes that are intersecting. So this cell, which this data point, this bucket, which this data point is mapping to, is the bucket 1, 8. Like this one is the bucket 3, 9. So these 2 are going to get mapped to 3, 9. So that's their bucket. That's their hash value. Now let's see that we have done this hashing. How do we answer a query? So let's say we receive a query point here. Okay, we want to find this most similar data object. So in this example, it's clear that there's a signed data point right here. If you only look at the cell of that query point, we are going to think that this guy is the closest data point. We are going to generate this as a candidate, which is not very good. So just because, I mean, they happen like to be right across the border. So to avoid these cases, what we do is that we generate a number of offsets, query offsets, which are like random points near this query point. So these are the offsets. And then to generate the candidates for this query point, we look at not only the bucket of the query point itself, but at the data points which are in any of the buckets of any of these offsets as well. So we look at this data point because it is in the same bucket as this query offset. We look at this data point because in the same bucket as this offset, and so on. And so using this, then in this example, we can actually find the closest data point. So let's see how we can implement this on MapReduce. The way we can implement it is the following. For a data point P, we just emit the bucket of P and P as a key value pair. For a query point Q, we generate all of these offsets, which are like random points around Q. And for each offset Qi, we output bucket of Qi and Q. Okay? And then what the reducer receives is that for each bucket value V, it receives all the data points whose bucket is V, and all the query points which have at least one offset whose bucket is V. And then the reducer just outputs the pairs of these data points and these query points as a candidate pairs for similarity search. So very simple algorithm. Again, the same question as the last one. Are we all good now? It's a pretty simple algorithm, right? And the answer is no. And the reason is to get good accuracy out of this algorithm we just saw, we need too many offsets. And each offset, like up here, is generating, one key value pair. So if you need too many offsets per query point, that means too much communication. So that's not very good. So let's see how we can solve it. Let's remember this picture that we had. So wouldn't it be good if we had these 4 cells, to map to the same reducer? It would be really good because then the reducer that receives these 4 cells would have all the data that it needs to answer, to find the most similar data point to this query point. But would we want to have this cell, like this cell right here, to also map to that reducer? Well, probably not, right? Because, I mean, it's not going to do any good to finding the answer to this query. So what does it mean? What it means is that we want the near cells to go to the same reducer and the far away cells to go to different reducers. So what does that remind you of, just this last sentence that I said? It should remind you of locality-sensitive hashing applied to the buckets. Because that's what locality-sensitive hashing does, right? I mean, like sending near stuff to the same buckets, in this case reducers, sending different stuff, in this case like different buckets, to different values, in this case like different reducers. So that gives the following algorithm. Pick another locality-sensitive hash function G, and let the map do the following. For each data point P, the map outputs the G of bucket P and as a key, and the bucket P and P as the value. And for each query point Q, we generate all the offsets, and we compute these G values of buckets of Qi, and we output and we emit like one such key value pair only for the distinct values of these keys. So we may have like 100 offsets, but they may generate only like 5 distinct values here. So we'll only like output 5 key value pairs here. So then what happens is that in the reduce, we are going to, for each value V, we are going to get all the data points whose bucket maps to V. When G applies to the bucket, it maps them to V, and all the query points which have at least one offset whose buckets maps to V using the second hash function G. And what the reducer does is that it indexes each of these data points at its bucket, and for each query point, it recomputes all of the offsets. So this is where we are getting the computational hit. Okay? So because we have lost the information about the offsets, we need to recompute them. So we need recompute the offsets at the reducer, and we recompute their buckets. And for any query point, we look at the data points in that bucket that any of the offsets map to, and we generate that query point plus and that data point as a candidate pair, and we just output these candidate pairs. So very simple algorithm, and here are some experiments with it. On the x-axis, we have the number of offsets. Okay, so the more accuracy that you want, the more offsets you need to have. And as you can see, like if you don't apply the second hash function, both the shuffle size and the runtime are going to go up very quickly as you increase the size the number of offsets. But if you do apply the second LSH function that we just saw, then the shuffle size stays very manageable, and it shows itself in the runtime as well. So it's pretty good. So this showed like that this was another like a somewhat more interesting example of the grouping. So the point in this example was that the grouping may not be always like trivial. So you may have to think a little bit about how you group things together. Now let's move on to the second second technique, and it's the technique of partitioning. So partitioning is essentially the classic idea of divide and conquer. So you divide your job into a number of smaller jobs and smaller tasks so that you can handle any one of them. And there is some people call the notion have defined this notion of curse of last reducer, which is you have all of your reducers have finished their jobs, and just one of them is still staggering and is just like doing a lot of work. So you want to avoid that when you do the partitioning. Let's see how we do it. So let's see an example. So we look at the graph clustering coefficient. So let's say you have an undirected graph with the vertex set V and the edge set E. And the clustering coefficient of a node V is the fraction of pairs of V's neighbors, which are neighbors themselves. Okay? So you look at any pair of neighbors of V and you see if they are neighbors themselves, and if they are, they contribute to the clustering coefficient. So the fraction of such pairs. And we also define delta of V to be the number of triangles incident on V. So let's see an example. Let's, like in this graph, small graph like down here. So for this pink node right here, what is the number of neighbor pairs? Well, it's just one because it has just one pair, right? And what is the number of triangles incident on it? Well, this is just this one triangle. And what is the clustering coefficient? Well, it has like one pair of neighbors and they are linked, so that's like 1 over 1, so that's 1. For this cyan node, it has just like one neighbor, so there is no pairs of neighbors, so the number of pairs of neighbors is 0, and there is no triangle incident on it, so that's also 0, and the clustering coefficient doesn't get even defined. And for this orange node, the number of neighbor pairs is, okay, so it has 4 neighbors. Any pair of those neighbors forms one of those pairs, so there's like 4 choose 2 or 6 such pairs. And the number of triangles incident on it is just 1. And the clustering coefficient is 1 over 6, because again, like it has 6 pairs, there's only this pair, which form a triangle, which are linked together. So that's always true, that the clustering coefficient is the number of triangles divided by the number of neighbor pairs. And why do you even care about this? Because it is a pretty useful feature in a lot of different applications, like in detecting spamming activity in web scale graphs. Like the spamming websites typically link to each other pretty heavily, so they have pretty high clustering coefficients. So that's a good, if you have a machine learning algorithm, this is a pretty good feature in it. Or in content quality in social networks, like so you have the content as a node, you have the users of the social network as other nodes. A user is linked to a content if the user consumes the content, and 2 users are linked to each other if they are friends or something. Then if a content has a high clustering coefficient, what it means is that most of the pairs of people who like that content are connected to each other. So that's probably a niche content. But if it's a content that is of broad appeal, then it's going to appeal to a lot of people who don't have any other relation together. So those pairs are not connected to each other, so it's going to have a small clustering coefficient. So you can use that as a feature for figuring out like what kind of content are we dealing with in a social network. And it shows up in a lot of other applications as well. So let's see how we can compute this. So as we saw, to compute the clustering coefficient, we only need to compute the number of triangles incident on each node. So here's a simple algorithm to do that. So the input is for each node, we have the adjacency list of the node. So that's the list of all of the neighbors of the node. And the map outputs 2 things. One is that it outputs all the neighbor pairs of that node. So for any neighbor pair, it outputs it as a key and V as the value. And then it outputs any edge as well as a key, and with a specific sign that doesn't show up anywhere else in the computations, like $, as a value. So here's an example. Like in this case, like if this node is V, you're outputting any pairs of neighbors. Like this pair is here, I know like this pair is here. So that's the key, and the value is the node itself. So this is a map step. And then the reduce step, for any pair of nodes U and W, it's going to receive any node that have an edge to both of these 2 nodes. So let's say these are these nodes. And also, if there is an edge between these 2 nodes, between U and W, it's going to receive this $. And if they don't have an edge together to each other, then it's not going to have this $sign in its input. So what the reduce is going to do is it's going to check if the $sign is part of the input. And if it is, then each of these is forming a triangle. Like each of these, like UWV1, UWV2, and so on. Each of these is a triangle. And it's going to emit VI and 1/3 to take this triangle into account for that node VI. And it's like 1/3 because each triangle gets counted 3 times from the perspective of each of its nodes or each of its edges. But in general, like it's just like looking at if there is this edge there, then it's saying that, okay, all of these are triangles and I need to count them. So very simple algorithm. So let's see if this is good. So again, it's a pretty simple algorithm. There doesn't seem to be anything wrong with it. But let's see. For each node V, the map step is outputting any pair of neighbors of the node, right? So that's like order of like degree squared of the node. So it's like dv squared over 2, if dv is the degree of the node V. So that's the number of key value pairs. I mean, that's not necessarily bad, but if a node is like has a degree like 50 million, then the number of those key value pairs that are going to get emitted is so crazy that even if we output 100 million pairs a second, which is never going to happen, then it will still take 20 weeks to just emit all of these key value pairs. And do such nodes actually exist? Yes, they do. Like Justin Bieber on Twitter is how many? Like 46 million followers. They do actually exist. So this is a problem. These heavy nodes are the problems in this algorithm. So, and it actually shows up in experiments. Like this is an experiment with live journal graph, and you see that most reducers finish very quickly, but some of them take much, much longer. So let's see how we can solve this problem. So the idea is the partitioning, as we talked about. So what we do is the following. We partition the nodes into P partitions. Let's say we call them V1 through Vp. And let's say rho of V is a function that maps each node to its partition. So it maps each node V to a number between 1 through P. Okay? And these partitions have almost equal size. Okay? Ideally exactly equal size, but they don't have to be exactly equal. And then what we do is that we solve the problem independently on each subgraph formed by the union of any triple of these partitions. And why do we look at triples? That's because any triangle is going to show up in exactly one such subgraph. We'll see an example and it will make it a little bit more clear. But the abstract idea here is that each triangle shows up in exactly one such subgraph, and then if we solve the problem on each of these subgraphs, then we count the number of triangles on each of these subgraphs, then consequently we can just add them up, add up those results, and get the number of triangles incident on each node in the whole graph. Let's see an example to make it a little bit more clear. Let's see this is our graph, and we are partitioning it to 4 partitions, 1, 2, 3, 4. So these are like 3 types of triangles that we have. Like this is one type of triangle, and all of these 3 nodes are in the same partition, in this case partition 1, and it is going to show up only in subgraph 1, 1, 1. So in the subgraph V1, union V1, union V1, which is just V1. We have this second type of subgraph, this green one, and it has 2 nodes in one partition, another node in another partition. And it is going to show up only in the subgraph corresponding to the triple 2, 2, 3. Okay, so that's like V2 union V3. And we have this type of triangle, which has every one of its nodes in a different partition. And these kinds of triangles are going to show up in subgraphs corresponding to 3 different numbers. So 2, 3, 4. Okay? So that's why we are focusing on these kinds of subgraphs for any I, j, k, which are like 1 less than equal I, less than equal j, and so on. So then what the algorithm that this gives us is the following, is that for each node, let's say we are again getting the adjacency list. And what the map outputs is that for each of these neighbors, it's going to send the edge between V and that neighbor to any of those partitions, to any of those subgraphs, triple subgraphs, which correspond to the row of V, the partition of V, the partition of that node, UT, and any other K for any K from 1 to P. So that's any other partition, any other subgraph that includes that edge. Okay, so it's going to send that edge to any such subgraph. So that's what the mapper does. And then what the reducer receives is that for any subgraph corresponding to I, J, and K is going to receive all of the edges in that subgraph. So it's going to just receive that subgraph essentially. Okay, and what it does is it just like solves a problem on that subgraph. And for each node x, it outputs delta sub ijk of x, which is the number of triangles incident on x in the subgraph formed by the union of vi, the partition like vi, vj, and vk. Okay, so that's what delta sub ijkx is. And as we saw, each triangle is getting counted once and only once in this part. So the final results can be computed as the number of triangles incident at each node is just the sum of the results that all of these reducers output. So we just sum them up. So that can be like a separate MapReduce job, but it's simple, so we are not going to look at it. So pretty simple algorithm. So let's make it a little more clear, like using an algorithm, using an example. So let's say we have a graph and it has 1 billion edges. Okay, and let's say we partition the graph to 100 partitions. So what that means is that each edge is going to get sent to 100 reducers. So because there are 100 subgraphs which have that edge, and so you remember, like, let's go up maybe. So remember here, like the subgraphs that this edge goes to is the ones that have like, the first one is the row of V, is the partition of the node V, the partition of node UT, and this K can be any number, okay? So any subgraph that includes this edge. So any edge is going to 100 reducers. So we are getting a factor 100 hit in the communication, so that we are a total of 100 billion edges are going over the network. But then the parallelism that we get is amazing because the size of each of these subgraphs the number of these subgraphs is around 170,000. That's a simple like combinatorial problem. Like, it's just a number of triples I, J, K, which are between like 1 and 100, and any like sequence of non-decreasing three numbers I, J, K between 1 and 100. So that's the number of subgraphs. So it's around, we can compute it, it's around 170,000. So the size of each subgraph is 100 billion edges, which are going over the network, divided by this number. So that's less than 600,000. So it's a pretty small graph, and each reducer can just handle it separately in parallel. So then here are some experiments with this algorithm. The reducer completion times are pretty balanced, unlike the example that we saw earlier with the previous algorithm. And here's a graph that shows the trade-off, again, between the reducer size and the shuffle size. So it again shows the trade-off between communication and parallelism. The more parallelism that you have, so you go here, so you reduce the you decrease the memory size of the reducer, so you get more reducers, the more communication you also need, and the other way around. And the total runtime shows an interesting effect. Like here, on the x-axis you have the number of partitions. So on the y-axis is the total runtime of the algorithm. So here what is happening is that the number of partitions is small. So the size of the graph that each reducer is receiving is large. So each reducer is like not able to handle it from main memory, so it's doing a lot of paging off of disk. So that's why it's slow. And on this end, we are doing too much communication. So here the communication becomes a bottleneck. So then there is a sweet spot around here that is the best point for running the algorithm. So far we saw the two trade-offs in MapReduce algorithms. I mean, one trade-off, but two ways. So between communication and parallelism, and we saw how we can go back and forth between each of these. So from communication, like reducer communication, and so I mean we can trade them off. So either way. So there is a third trade-off governing MapReduce algorithms, and that is the trade-off with approximation. So getting a little bit of hit in the approximation of the algorithm. So instead of like having exact algorithms, allowing a little bit of approximation can go a long way in improving both the communication and the parallelism of the algorithm. Let's see an example of that. So actually, let's see first a technique to do that. So the technique, one technique to achieve this, to do this trade-off between approximation is the technique of filtering. So what we do in the filtering technique is that we say, okay, so if the data is, if the size of the problem that we are dealing with is too large and we cannot handle it, then the idea is essentially like to bring the data from the realm of big data to the realm of small data. And the way we do that is that we quickly decrease the size of the data in parallel in a distributed fashion while maintaining the features of the data that we need to actually compute the result that we want. Okay? And then we solve that smaller instance of the problem just locally. And let's see an example of that. Let's say we want to compute, so the problem is the densest subgraph. So let's say again we have a graph G with vertex set V and edge set E. The goal is that we want to find the subset of the nodes like S, which has the highest density. And the density is defined as the number of edges between any pair of nodes in S divided by the number of nodes in S. So in this example down here, for instance, these nodes in red are the densest subgraph, and that subgraph has 6 nodes, and there are 11 edges between the pairs of those red nodes. So the density is like 11 over 6. And why do we care? Because finding dense subgraphs also shows up in a lot of different applications. Like in protein-protein interaction networks, dense subgraphs typically correspond to meaningful functional modules. So that's why we would want to find them. Or in social networks, they correspond typically to communities in the social network. Or again, like in the web spam detection, again, for the same reason we saw this before, like the spam websites typically link very heavily to each other, so they form a strong community, they form a dense subgraph. So let's see how we can do this. So there is a exact solution for this problem using linear programming techniques. But the problem is that it is very hard to scale. Like till recently, it was not known actually how to scale. Now it is known how to scale it, but it is still doesn't give a very practical algorithm. So let's see how we can get around this shortcoming. So here's an intuition, like along the line of the filtering technique. So what does the filtering technique say? The filtering technique says get rid of anything that doesn't help you with computing your answer. So let's see what things here we can get rid of that don't matter in computing the densest subgraph. Well, the nodes. So here's an intuition. The nodes with degree not much larger than the average degree of the graph, they actually don't matter. Let's see why that is. Let's say you have a graph S, which has density 100. So let's say this is your graph. So the average degree of this graph is 200, because the average degree is twice the density. So what this means is that the size of the graph is also at least 201, because the average degree is 200. So there is at least one node which has degree 200. Well, that one node, like this guy, for instance, let's say here, is connected to 200 other people. So that's 201 nodes in S right there. And let's say we have a node V in S whose degree is 205. So it's slightly larger than the average degree. Now let's see what happens if you just remove this node V from this graph. So what happens to the density? So the density is like the number of edges in S minus V divided by the size of S minus V. Well, the size of the number of edges is ES minus 205, because when the node V gets removed, all of these edges also go away. So we lose 205 edges, and then we lose one node, okay? But E of S from here, we know that is equal to 100S. So that's 100S minus 205, or S minus 1. That's equal to 100 minus 105, or S minus 1. And we know the size of S is at least 201. So we plug it in here. So that gives us the density is at least 100 minus 105 or 200, which is 99.5. So the density, the main point here is that even if you didn't follow the math here, the main point is that if we remove this node, the density of the resulting graph is either going to be larger than 100, or if it's going to be smaller, it's not going to be much smaller. We are going to be at most like 0.5. We are going to give away like 0.5 out of the density of 100. So it's like very small. So that's what that intuition means, that these nodes don't matter, so we can just get rid of them. So that gives this algorithm, actually. So the algorithm is as follows. We choose a small number like epsilon, so it can be like 0.5, 0.1, 1. And then we iteratively remove all the nodes whose degree is less than or equal 1 plus epsilon times the average degree. So we start with a graph. We remove all such nodes. We get a new graph. Then we remove, in that new graph, we again remove all such nodes. Notice that the average degree changes. And we do this until we remove all of the nodes. And what happens is that we keep the densest intermediate subgraph that we see along the way as our approximation for the true densest subgraph. Let's see this algorithm in action, actually. So this is the graph that we saw before. So we have the density of this graph is equal to 19 over 12. Now, we remove anything whose degree is less than the average degree. So these are these nodes, so we just remove them. So we get this subgraph. And the density of this graph is 9 over 5, and it's bigger than the density of the previous graph. So it's the highest density that we have seen so far. And the average degree is 18 over 5, so we remove any nodes with degree less than that average degree. Those are these two nodes. We do the same thing here, and we remove everything. And the final result that is like the densest subgraph that we saw along the way while we were doing these removals was this subgraph, and it has a density of 9 over 5 or 1.8. And we saw before that the true densest subgraph was this subgraph. And it has a density of 11 over 6. So this is 1.8, this is 1.83. So it's pretty close. So we removed this node, and we shouldn't have. But it's not a big deal. And the MapReduce implementation of the algorithm is pretty simple. So for each of these removals, for each of these steps, we need to compute the number of edges and the number of nodes. So that gives us the average degree. And we need to compute the node degrees for each node. Each of those is like a simple word count, so I'm not going to go through it. And to remove, and then when we compute the threshold, which is like the average degree, then each node can independently decide, given that number, each node can independently decide if it should go to the next round of this algorithm or not. So that's another like map step. You don't even need a reduce step. Then the experiments with this algorithm show that the approximation factor that it gets is pretty close to 1 in practice. And as you see here, it reduces the size of the graph. So this is like the number of iterations performed by the algorithm. This is the number of nodes, and this is the number of edges. So this is with the Yahoo Instant Messaging graph. It has like 600 million nodes, and like between like 6 and 7, like 6.5 billion edges. So as you see, like the number of both the number of nodes and the number of edges are going down very, very quickly. So that's the whole idea in the filtering technique. Notice that like once we do like a bunch of like these iterations and the size of the graph is small, we can even apply the linear programming technique that we had that I mentioned to find the exact densest subgraph. But here like we're just going all the way using this algorithm. So that also shows the filtering technique and how we can trade off the parallelism and the communication with a little bit of approximation, allowing a little bit of approximation in the results. So yeah, as a summary, what we saw was the trade-offs governing the MapReduce algorithms, and more generally, any like scalable big data algorithm between communication, parallelism, and approximation. And we saw 3 techniques to actually make these trade-offs efficiently. So those were the grouping, partitioning, and filtering techniques. And with that, I conclude my talk and open it up to questions. All right, thank you.